Hello, North Tahoe High students. In this short video, we're going to take a look at how calorimetry works, hopefully be able to solve the problem that we just were left off with that the woman in the lab coat gave us. Her task was to find the specific heat capacity of cadmium. I'm going to show you how to make use of the numbers that she gave us. We're going to use put together three concepts that we've learned. The law of conservation of energy, which says that energy cannot be created or destroyed. The idea that when we're talking about heat, it's a transfer of energy. So transfer always involves two things: a system and its surroundings, what we're going to use in chemistry, and then the mathematical description of how heat is transferred has to do with this. When we saw it in our books, it looked like this. The specific heat capacity, C, is equal to the heat transfer into or out of a system divided by the mass of the substance in the system and the change in temperature of the substance. A lot of times we might want to use it this way, just solve it algebraically for the heat or the energy transfer, and it would look like this: specific heat capacity C times M times delta T. So if we look at this picture, this brave woman in this very cold body of water, we can get a sense for how calorimetry is going to work by putting all of these things together. If we consider the woman to be the system and the water the surroundings, there's a transfer of energy or a flow of heat. Obviously, the woman is at a higher temperature than the water. Body temperature's much warmer than close to freezing water. So the direction of heat transfer would be away from the woman into the water. Conservation of energy then is telling us that the energy that the woman loses, if it cannot be created or destroyed, has to be absorbed by the water. So mathematically that means this: Q, and I'll just write it this way, of W lost, that's the energy that the woman lost, has to equal Q of H2O gained. Now, the woman loses energy, so typically that would be a negative value, but we're going to keep it simple mathematically today, and just think about the absolute values of heat. So we're going to say the woman loses positive heat, and the water gains positive heat. Now, it can't really carry out an experiment in a lake like that for a couple of reasons. A, the woman is generating heat while she's alive, and B, that lake is just too large to make measurements, and we could lose heat to the environment and to the atmosphere. So we need to devise a relatively simple device called a calorimeter that will make sure that the only heat transfer is between the system and the surroundings. So in the case of the video that we saw earlier, it would be the metal and the water. A foam cup does that really well, so we don't have heat leaving into the room or entering from the room either. So these are both pictures of calorimeters that we would use in the lab. A thermometer placed in a styrofoam cup here. You're going to see a styrofoam cup here then in the next slide. Okay, so let's replicate what that woman did in the experiment and see how we're going to use our knowledge to figure out what is the specific heat capacity of this metal. So we got a chunk of metal down here. It just came out of the hot water bath. So its temperature is 100 degrees Celsius and its mass is 50 grams. And we're going to put it into a calorimeter that's already full of water. And we have been given the fact that the mass of the water is 200 grams and the temperature of the water is 20 degrees Celsius. So we could go ahead then and plop that mass in there. And we're going to notice something with the thermometer and the calorimeter that's probably pretty obvious to some of us. What we'll notice is the thermometer of the temperature of the water increases. So the temperature of the water, of course, increases because the system, which might be the rock, loses heat to the water. So the water temperature goes up, but the rock's temperature goes down. So let's just say then that this is the final temperature. The water warms up from 20 degrees Celsius. It warms up to a temperature of 24 degrees Celsius by virtue of putting that hot rock in there. If the final temperature here is 24 and we leave that in the rock in there, the rock's also going to come to 24 degrees Celsius, right? They come to equilibrium if we were to watch this long enough. So both of the final temperatures would be 24 degrees Celsius. So let's take a look at what that means in terms of their temperature change. Remember, delta T is always the final minus the initial. So the temperature change for the metal, which I'll call M, and I've also been calling a rock, would be its final temperature, 24 degrees Celsius, minus its initial temperature, which was 100 degrees Celsius. So it cools down and has a negative temperature change of negative 76 degrees Celsius. And again, for today, we're just going to keep it positive, so we'll take the absolute value, so 76 degrees Celsius. Do the same thing for the water. Temperature change for the H2O. The final temperature is 24 degrees Celsius. The initial temperature, right up here, was 20 degrees Celsius. So the temperature change for the water is positive 4 degrees Celsius. All right, so let's put this all together then. When all is said and done, we did have an energy transfer from the hot piece of metal to the colder water. And the energy transfer then traveled from the rock, which we might have thought was the system, to the surroundings water. So that was Q. Conservation of energy says this, that the heat gained by the water has to equal the heat lost by the metal. So we're going to use absolute values. QH2O equals Q metal. And our equation that describes this with temperature change and specific heats looks like this. We saw that on the first slide, solved for Q. So I'm going to replace or put in some numbers here. We're going to have one unknown. Okay, so down here in blue, I've replaced everything with the known values. This would have to be known going in, that the specific heat of water is in fact 4.18 joules per gram per degree Celsius. We knew the mass of the water, we knew the temperature change of the water. We knew the mass of the metal, we knew the temperature change of the metal. So we have one unknown, that's the specific heat of the metal. So we do a little bit of algebra and we solve for it. The C of metal, specific heat of metal, should be in this case about 0.88. And the units of that again would be joules per gram degree Celsius. So what I'd like you to do right now is go back, use the information from the video and the woman with cadmium, see if you can find the specific heat of cadmium from her experiment. Look up online what the specific heat of cadmium should be according to literature. See how close she got with those numbers.